for this lesson, a lot of the questions you can just apply the fundamental counting principle, but you can also apply the permutations formula if you want. Let's see how you guys do. It's just pretty much a little bit of review from yesterday. So we have the word oranges. In how many ways can all of the letters of the word oranges be arranged if, first question, there's no restrictions? Let's just review the fundamental counting principle. Okay, so how many letters do we have in oranges? 2, 4, 6, 7 letters. So 1, 2, 3, 4, 5, 6, 7. So for the first letter, how many choices do we have? 7. And then 6, 5, 4, 3, 2, 1. So rather than writing this out, how could I express 7 times 6 times 5 times 4 times 3?
7 exclamation mark.
Which is called
7, yeah, I don't know.
7 factorial.
Yeah, we're all stupid.
So we have 7 elements and we're taking 7 at one time. Okay, so it equals n factorial, 7 factorial. 7 factorial, if you calculate that, do you guys remember which buttons to press? So you go 7 and then math over to PRB. Number 4 is your factorial button. What do you get?
5,040.
540 or 5040.
Usually that you're
All right, next one. The first letter has to be an N. Okay, let's use the fundamental counting principle again. So if the first letter has to be N, how many choices do you have for the first letter?
1,
1, and then?
6, 5, 4.
So this is just really equal to 6 factorial, which is 720. Just ahead of the game. All right, the vowels must be together in the order O, A, E. So we have O, A, E, and then we have 4 remaining letters. Is that the only spot that OAE could be located though? Okay, so first we've used 3 letters, OAE, then we have 4, 3, 2, 1 left over. But OAE could be the second letter in. Okay, maybe I'll just put a box around OAE. And then we have 3 left. Started with 4, then 3, then 2, then 1 choice. Okay, or there could be 2 letters first, and then OAE, and then 2 letters following. So that'd be 4, 3, 2, 1. And then we could have 3 letters first, 1, 2, 3, and then OAE, and 1 following, with 4, 3, 2, 1 is our choices. And the last scenario is if OAE takes the last place. Okay, so 4 letters first, and then OAE. 4, 3, 2, 1. So basically we're seeing 4 factorial how many times? 5. So what's 5 times 4 factorial? It's 5 factorial.
Oh.
Remember? 5 times 4 times 3 times 2 times 1. That could be written as 5 times. What's 4 factorial? 4 times 3 times 2 times 1. So if we're multiplying by 5 different ways, we can arrange OAE. Then it's 5 times 4 factorial. We get 5 factorial. So a shortcut to questions like this is if the letters have to be in a specific order, you can just look at, this is kind of like one place. And then we have 2, 3, 4, 5. There's 5 spots that need to be filled. Okay, so 5 factorial. Because there's 5 different things that can be arranged. Okay, if you're grouping OAE as one element. Okay, in how many of the arrangements of the letters of the word brains are the vowels together? So for brains, we have 2 vowels. And we have 2, 4, 6 letters. 2, yeah, 6. Okay, so there's going to be 2 cases for this. What if we had AI, and then, so that's 2 of the spaces, and then we had 1, 2, 3, 4. If AI is together, and then I have 4, then 3, then 2, then 1, is that not pretty much exactly like the question we did? Okay, AI could be in the 2nd place, or the 3rd, or the 4th, the 5th. So really, this is like 5 factorial. Exactly like what we just saw above. Yeah?
Can it be IA as well?
Yes, that's the OR case. So this is one scenario. Or, what does OR mean? Add. Good. Or we could have had IA. Okay, and then 4, 3, 2, 1. Which is also 5 factorial. So we have 5 factorial plus 5 factorial. And sorry, we didn't actually calculate 5 factorial. It's 120, right? Okay, so we have 120 plus 120. That gives us 240. Now I'm going to look at it in a different way. Now IA, that's really like 2 factorial, right? Because it's either I or A, and then the remaining one. So that could be like 2 times 1. And then we have the 4 remaining letters. 4 times 3 times 2 times 1. So could we not just go 2 factorial times 4 factorial as well? What do you get when you multiply that? What do you get?
48.
Let me do it again.
Okay, hold on. No, you should get 48. What did I do wrong? 2 factorial.
Should be a 5 factorial instead of a 4.
In that case, yes, because you can arrange the vowels in different places. So when you go 5 times 4, that's 20 times 3 is 60 times 3. Yes, sorry, it should be 5 factorial because the vowels, don't forget, just like we saw above, it can be placed in the 1st place, the 2nd, 3rd, 4th, or 5th. So it's actually 5 different possible ways of arranging that. So 2 factorial times 5 factorial. Okay, so you can do this 2 different ways. You can go through the process of fundamental counting principle, or you can do it in one way using the fundamental counting principle. All right, find the number of permutations of the letters in the word kitchen. Okay, the first condition is the letters KCN must be together, but not in that particular order. So similar to the vowels we just looked at. Okay, we could have, maybe I'll do it this way. So it's KCN, some sort of combination of KCN, any order for that one. Okay, that means we have 3 choices, then 2 choices, then 1 choice. Okay, that's for KCN. In other words, 3 factorial. Now how many letters do we have in kitchen?
7.
7 letters. So that means we have 1, 2, 3, 4 spaces left. So 4, 3, 2, 1. That's pretty much like 4 factorial, right? But how many ways could I arrange KCN and the remaining letters? 1, 2, 3, 4, 5. So rather than putting 4 factorial, I'm going to put 5 factorial. Because KCN can take the 1st place, the 2nd, the 3rd, the 4th, or the 5th. Okay, another way to think about this is You could go 3 factorial times 4 factorial, but there's 5 ways to do it, so you could also just multiply by 5. But what is 5 times 4 factorial? 5 factorial. So 3 factorial times 5 factorial. What do we get? 720? Now this next case is unique, and it's a case that you'll want to remember. Okay, the vowels must not be together. So to figure out this one, we're going to look at the case where there's no restrictions. And we're going to subtract the case if the vowels were together. So if there were no restrictions, we have 7 letters, we're going to take all 7 at one time. We have 7 factorial. Now let's look at the scenario if the vowels are together. So in kitchen we have vowels I and E. So that's going to be 2 factorial. Okay, and then we have 5 letters left, right? Okay, so 5 times 4 times 3 times 2 times 1, which is really like 5 factorial. But how many different ways could I arrange the IE within those letters? Well, it could take the first, the second, third, fourth, fifth, or sixth place. So there's 6 different ways. So really we're multiplying 2 factorial times 5 factorial times 6 different ways that we could arrange IE. So what could I write this as instead? 6 factorial. Okay. So we have 7 factorial minus 2 factorial times 6 factorial. 7 factorial is 5040. And 2 factorial times 6 factorial, we get 1440. So subtract and you get 3600 different ways where the vowels will not be together. Okay, one thing I haven't been using yet is the permutation notation. So I'm going to use a few different ways to solve this next example, just so you're seeing it as well. In how many ways can 3 girls and 4 boys be arranged in a row if no 2 people of the same gender can sit together? So let's just start by using the fundamental counting principle. We have boy. How many in total? 7? Okay, so 1, 2, 3, 4, 5, 6, 7. So we have boy, girl, boy, girl, boy, girl, boy. There's 4 boys, which is why I started with boys. Okay, so we had 4 boys, then 3 boys, then 2 boys, then 1 boy left over. And for the girls, we started with 3 girls that we could pick to sit in this first spot. And then we only had 2 to pick from, and then 1 to pick from. So for just the boys, we have 4 times 3 times 2 times 1. 4 factorial. And for the girls, we have 3 times 2 times 1. So 3 factorial. If you guys multiply 4 factorial times 3 factorial, what do we get? $144. So the other way we could have solved this, we had 4 boys, and we had to pick 4 boys. Okay, and we had 3 girls, and we had to pick 3 girls. So if you multiply this, I'll show you how you can do this in your calculator.
Can you explain that notation? I don't completely understand it.
So NPR, this is the total number of elements and R is the number you're taking at one time.
Okay.
Okay, so if you had 4 boys, we're taking 4 at a time.
So, like, in what way would it not be 4?
Say if you had the word math. Let's just use maths. Okay? And I wanted to create a 3-letter word. Then I could go, well, there's 5 letters total, and I'm only going to pick 3 of them.
Okay, that makes more sense.
Okay?
And then that would give you like all the options for that, only using 3 letters at a time.
Yeah, so this is just another way of writing 5 times 4 times 3.
Oh, okay.
Okay, which we're going to get into thought we were going to get into in the next lesson. Did we do that last lesson?
Yeah.
That's what I thought.
Yeah, I kind of, like you explained it yesterday, I just didn't
Yeah.
get it.
Okay.
But that makes more sense. Yeah.
Sorry, we did lesson 2 at the last class, so I was trying to remember if I did that today, or which day I did it with, what class. Okay. So here, do you guys remember how to get the P, the permutation in your calculator? So I would go 4 and then math over to probability, and number 2 is your permutations button. So 4, pick 4, and then enter. You get 24. Okay, and then I would have to multiply by 3, pick 3. So 24 times 6. We get 144. So for the next one, 6 actors and 8 actresses are available for a play. Only 4 male roles and 3 female roles are available. How many different cast lists are possible? Okay, well we have 6 actors. How many male roles are there?
3, 4.
4. So we have 6 actors. We're only going to pick 4. Okay, and using the fundamental counting principle, there's 4 slots. We had 6, then 5, then 4, then 3 guys to choose from. Okay, we're going to multiply this by the female roles. So we started with 8 female actresses. We're only going to pick 3 female roles. Okay, so that would be like 8 times 7 times 6. So I'll let you guys decide how you want to calculate it. But you're multiplying the male role times the female role. Okay, you should get 120,960. Did we get that?
Yeah.
So now we're going to just look at what happens if we have permutations with repetition. So in this one we have the word rows. Maybe I'll start from the beginning. So the objects in each set were all different, but what happens when there are letters which repeat within the same word? So we're first going to look at just rows as rows. There's no repetition of letters. Okay? As you can see, if we were to rearrange all the 4 letters, R-O-S-E, these would be the list of the combinations of the orders. Okay? In simple terms, we could have just used the fundamental counting principle. Okay? It could have been R-O-S-E, 4 choices. And then we only have 3 letters, and then 2, and then 1. So that's really like 4 factorial, or as they've written, 4, pick 4. 4 letters total, we're going to pick 4 of them. And all of that results in 24 possible arrangements. Okay, but what happens if we take the letter E and we exchange it with S? So now instead of Rose, we have the word Ross. Well, you're noticing what's going to happen is some of the words are going to be exactly the same. Okay, and if I were to go through and circle all the ones that were the same, we would get pairs. Okay, so how many pairs would you have in 24? You'd have 12. Okay, so now we only have 12 different arrangements. So what's happening is we're dividing by the number of pairs that are possible. So in this case, we started with 4 factorial, and now we're dividing by the number of pairs factorial. Okay, so 4 factorial divided by 2 factorial. And what would happen if we had our SSS? Okay, so 3 of the letters are S's. Well, instead of 24 combinations, we would have to highlight all the pairs that are occurring, and we'd go, or in this case it wouldn't be pairs because there'd be 3 that are exactly the same, and we can see that, hold on, our SSS, I guess we have 4 that are, no, these are the same, sorry, these are the same. And then, it's not really ordered. Let's circle these then. SRSS, you see any more? So how many do we have? 6, 6, and then 6, and then another 6. My explanation isn't really making or working out in this case, but what I'm trying to say is you're dividing by the number of letters that repeat. Okay, so in the last example we had 2 letters that repeated, so we divided by 2 factorial. Here we have 3 letters that repeat, so we're dividing by 3 factorial. So notice the 24 original arrangements now become 4 different arrangements, 4 matching sets of 6 4-letter arrangements. Arrangements like the following. From the list all become one arrangement of R, S, S, S. So in other words, we only have 1/6 of what we had before. Okay, and that's where we're getting the 3 factorial from. Okay, so if we had 24, but now we have 4 groups of 6, that's 1/6 of what we had before. Okay, so we just divide by what we're repeating by. And I'll just go to the next page. This is the general rule for repetition. Okay, so you take the total number of elements or objects, and you're going to divide by the number or the letters or whatever is repeating factorial. Okay, so let's try and we'll look at Vancouver for instance. Are there any letters that repeat?
Yes.
V's. Okay, so we have 2 V's. And total letters possible, we have 3, 6, 9 letters. Okay, so we would go 9 factorial divided by 2 factorial. And figure out how many different permutations or arrangements we could have for that. So 9 factorial divided by 2 factorial, you get 181,440. How many letters are in mathematical? Do you get 12? Okay, now let's just highlight some of the letters that repeat. We have 2 M's, 3 A's, and 2 T's. Okay, so we have 3 different letters that repeat. To figure out the number of possible arrangements that we could have, we take the total number of letters, 12 factorial, and we're going to divide by the letters that repeat factorial. So we have 2 M's, 3 A's, and 2 T's. If you were to calculate this in all one go, just make sure you put brackets around the denominator. Okay, this is a biggie. We get 19,958,400. So you probably wouldn't have to or want to write out all the combinations, would you? And I'm going to correct myself. I shouldn't say combinations, arrangements, okay? Or permutations. This next one we have to think a little bit about. Brett bought a carton containing 10 mini boxes of cereal. There are 3 boxes of cornflakes, 2 boxes of Rice Krispies, 1 box of Cocoa Pops, 1 box of Shreddies, and the remainder are Raisin Bran. Over a 10-day period, Brett plans to eat the contents of 1 box of cereal each morning. How many different orders are possible if on the first morning he has Raisin Bran? Well, let's look at how many total. Okay, so we have 10 boxes of cereal. And let's just make a little tally or total of what we have. So we have 3 of cornflakes. We have 2 Rice Krispies. 1 Cocoa Pop. 1 Shreddies. And the remainder are Raisin Bran. So how many are Raisin Bran? 3. Alright. Over a 10-day period, Brett plans to eat the contents of 1 box of cereal each morning. But the question is, how many different orders are possible if on the first morning he has Raisin Bran? So day 1, he has 1 box of Raisin Bran. So now we have to look at days 2 to 9. So if he's already made that choice, 1 box of Raisin Bran has been consumed on day 1, that was 1 choice. So there's only 1 option for day 1. So we're going to go 1 times whatever the rest is. Okay, how many days do I have left? 9, or 9 boxes of cereal, right? So I have 9 factorial divided by all the boxes that repeat. So I had 3 boxes of cornflakes. I had 2 boxes of Rice Krispies. And before I go and put 3 boxes of Raisin Bran, I have to remember that I already ate 1 box, or Brett did. So there's only 2 boxes of Raisin Bran left. And if you want to just put, this is for cornflakes, Rice Krispies, and Raisin Bran. Then if you look back, you'll know why it was a 2 instead of a 3. Okay, so when we calculate that, don't forget to put brackets around the denominator. And there should be 15,120 different arrangements of how Brett can eat his cereal. You guys were really curious about that, weren't you? So you're likely to travel from A to B in your life, and if you're ever wondering how many routes are possible, you can use factorials or permutations to figure that out. So Paul and Catherine are considering the following problem. Find the number of routes from A to B if routes must always move closer to B. So Paul arrived at the correct answer by tracing 10 routes. So he went 1 route, 2 routes, 3 routes, 4 routes, 5 routes, and then etc., etc. He kept doing that and figured out there was 10. Okay, but say you have a bigger grid. Are you really going to want to trace out all the possible ways? Maybe, if you forget what you're supposed to do. But Catherine chose a different way. She developed a quicker method. She realized that travel from A to B involves moving 3 units east and 2 units south. Okay, even if I did a different combination, this is 1 unit east, and then say I moved 1 unit south, and then 2 units east, that's still 3 units east in total, okay? So basically, she's figuring out that the answers to the problem is a number, it could be any order of east, 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 south, south, okay? So going east, there's 3 possible ways, and going south, there's 2 possible ways. So in total, we have 5 items, okay, or 5 boxes, we could say. Okay, 3 to the east, 2 to the south. But we're repeating south twice, okay? We have a south, south, so we have to divide by 2 factorial. And we're repeating east 3 times, so we have to divide by 3 factorial. When you plug that in, you should get, again, 10 roots.